All right, so let's just quickly check whether my mouse here is responding. Okay. So last time what we did was came up with a bunch of partial differential equations that define how a body, what are the conditions for a deformable body to be in equilibrium. So the way we went about that was take any deformable body, take some finite neighborhood of that body, draw the free body diagram, which includes all the surface tractions and all the body forces acting on it. We used the divergence theorem that holds for any tensor field to come up with the condition that divergence of Cauchy stress plus body force equal to 0 has to hold at all points in the deformed configuration for a body to be in equilibrium. And this was nothing but the sum of forces at each and every point in a deformable body has to be equal to 0. We also saw that for sum of moments to be equal to 0, we found that the condition was that the Cauchy stress has to be symmetric. And finally, that allowed us to write the conditions required for equilibrium as those two: divergence of S plus B equal to 0, Cauchy stress being symmetric everywhere in the deformed body. That was the undeformed. This is a deformed body. And the Cauchy stress traction relationship. This is stress traction relationship has to hold at every point on the surface of that body. So that's the boundary. There are two conditions on the domain, every point within the body, and there's this one condition on the boundary of the body for equilibrium. And I mentioned last time that there are these two parts of the boundary usually where either displacements are specified or tractions are specified. You can't specify that I want the traction on this particular deformed body, let's say at this end, to be whatever force per unit area, like 100 newtons per meter square, and I want the deformation at this point to be 0.1 inches. You can't do that. So you can specify only either tractions or displacements. So I think that's about where we were last time. So let's take a quick couple of examples today about how to judge whether a body is in equilibrium or not, and also get into some large deformation interpretation of the stresses, the Cauchy stress, and how it relates to something called Kirko stress. So first, these examples. Simplest example, a rigid block under self-weight. We are going to try to write out the stress. The stress field here is given to us, but we are going to try to write out all the equilibrium conditions. One thing I'll point out here is that the body force given here in this example in the book is minus rho E3, where actually rho is supposed to be specific gravity, meaning now sometimes we call that specific gravity as gamma, which is rho times g, where rho is the density and of course g is acceleration due to gravity. So the more common notation would be that B vector is equal to minus rho E3, where E3 of course is in the vertical direction of the gravity. So that's a body force, which is body force density. That's a distributed force per unit volume. If you multiply that by the volume of this block, that would be the total weight of this body. So I'll change those things here as well. And instead of calling it rho, I'll call it gamma. And out here in this expression as well, we are saying that the stress field at any point x in this body is going to be given by gamma times x minus 3 or x3 minus h in the direction in the basis E3 diad E3. All the other stress components are 0, but one of those components is non-zero. So here's a question: what type of state of stress is this? we looked at three types of states of stress: hydrostatic and pure shear, and this is uniaxial. It has uniaxial stress in the 3 direction. Every other stress component is 0. So we are going to verify, first of all, the governing differential equation, for which we need divergence of S. So divergence of S, hopefully you all remember, given a stress tensor S, we can take S dot with grad operator. Right? Grad operator has those three components: partial of partial x1, partial of partial x2, partial of partial x3. So those we list out here. When we act this stress tensor um, on that grad operator, that's nothing but divergence of stress is nothing but this S dot grad. Maybe I'll write it below here. Um, so if we do that, what we get is the first two components 0. The next component derivative with respect to x3 will just give me this gamma. And of course, body force, we already know, is equal to minus gamma E3. So if we sum them up, divergence of stress, that's gamma, and body force is 0, 0 minus gamma. So clearly they would cancel out and you would get 0, meaning that this particular stress field makes sure that every point in this body is in equilibrium. Okay, this is a point-wise check. This was a stress field, so we calculated divergence at every point in this body, and we added the body force to every point in this body and made sure that that was equal to 0. So that makes sure that every point in the body is equal to 0. We still have to verify the boundary of this body. The boundary of this body has 6 faces, so we're going to have to check those conditions, the stress traction condition on all of these 6 faces. So for that, we'll take the unit normal, plus minus E1, plus minus E2, and plus minus E3 on all of these 6 faces, and let's see what that gives us. For faces plus minus E1 and plus minus E2, which are the 4 vertical faces, right? On that, if I act this stress tensor, what do I get? 0 tractions. So indeed, S acting on N would give me 0 vector, 0 tractions, and there is no externally applied traction on that face. So it makes sure that those 4 faces are self-equilibrating. For the face, for the top face, which is x3 equal to h, we have E. The normal is plus E3. For the bottom face, the normal is minus E3. Those are those two. For the top face, S acting on E3 when x3 is equal to h, immediately that goes to 0, right? So indeed, on the top surface as well, my traction is 0, because there is no externally applied traction on the top face. But is there traction at the bottom face? The traction from the bottom face, where is that coming from? The reaction of the floor, right? The body has its weight. The ground is applying traction back to the bottom of the face. So that indeed is the external force applied to this block. So I get S acting on E3, and that can be represented as x3 would be 0. I would get minus gamma h, and acting on 0, 0, minus 1, that would give me 0, 0, gamma h. Okay. And I think I'm going to change all of these rows to gammas as well. So this is gamma h, gamma h, gamma h. And just to sort of make this even more clear, if you look at some height between, so that was the traction gamma h that I talked about. This was this last phase. But what we're going to do now is to try to imagine half of the block. We're going to take imagine the top half and the bottom half of the block and see whether we get each of those parts to be in equilibrium or not. So for any height x3, if you take that, imagine that cut at any height x3, what you would get would be on the bottom face and the top face, you would get, maybe I should write that out here. For an intermediate phase, again the normals are plus minus E3, and the stress tensor is the same. So S acting on N would just would be given by the components 0, 0, and the third component up here, that's gamma x3 minus h. So 0, sorry, gamma times x3 minus h. That's the traction, and I obviously need the plus minus sign in here. Plus minus that. So if you look at the top half of the body, okay, the normal on the bottom face is minus E3, right? A normal on the bottom face is minus E3. If you take this quantity out here, would this be negative or positive? X3 minus h for let's say this height is x3. It would be negative, and since the normal on the top of the bottom face is minus 1, therefore negative times negative would become positive E3 direction. So gamma times x3 would be pointing in the positive x3 direction. That is the traction that is just supporting half of that block, and that would be equal to the traction that the top of the block is applying on the bottom block immediately, that you get either from that Cauchy reciprocal theorem or the Newton's third law. So no matter where you take that cut, the top half and the bottom half would be, of course, in equilibrium, which we already checked because we made sure that divergence of S plus B is equal to 0 everywhere in the body, and that all of the 6 faces are also in equilibrium. So that's just a very simple example of how you would check whether a body is in equilibrium or not, given the stress field. And if there are some other types of problems where you might be asked that, given this stress field, tell me the body force that would be required for equilibrium. That's actually one of the problems on your homework. In order to solve problems like that, you would again just take the derivative or the divergence of S, and B would just be the negative of divergence of S to make sure that it goes to 0. Okay. Any particular questions on this problem? I think this. So even though this looks very simple, I think it's important to understand that the stress field is varying through the height of the body, and that's why the derivative of the stress field is constant. It varies linearly, so derivative is constant and make sure things are in equilibrium. Here's another example. So let's consider this solid deformable sphere floating in a pressurized chamber, and let's say that the pressurized chamber is out of the effects of gravity, so somewhere in space. So that when we take different points on the surface, those different points normally have different pressures, right? If I have a finite sized body that I've submerged in underwater, top surface of the body has lesser pressure, bottom surface has greater pressure. But if we neglect the effects of gravity, then the entire surface has the same pressure. So I'm saying that let's assume that the stress field is a constant stress field which is given by minus P identity tensor for every point in the body. Okay, and if we want to verify whether this is in equilibrium or not, we are going to again check the governing differential equation. Divergence of S is plus body force equal to 0, whether that's satisfied or not. First question, what is divergence of S for this particular field? 0. It does not even depend upon X, right? P is a constant, so it does not depend upon X, immediately means this is 0. 0 vector. The body force, there is no body force because we just said that it is out of the effect of the gravity. So indeed body force is also 0, and which means that the governing differential equation everywhere inside the body holds. And as I said before, that is not sufficient to make sure that the body is in equilibrium. We also have to check the boundary conditions. So what boundary conditions do I have here? What should I check? What condition do I need to check? I need to check Tn is equal to Sn on for all points. By the way, this symbol is for all. I don't know if I mentioned that. For all x in an element of, just to be precise, I should also write that as a deformed equilibrium. So in the deformed body B, and for all points x in the deformed surface of that body A, where in this particular case, as I said, A sub D is null, meaning there is no point at which the displacements are specified. The entire boundary is the Neumann boundary, A sub n. How do I check this? What is n for this particular case? Okay, so indeed n is any radial vector. So n is equal to x divided by magnitude of x. That's the unit radial vector. And if I take minus p acting times I acting on x divided by magnitude of x, I get that traction is equal to minus p times x divided by magnitude of x, which is nothing but minus p times n. Is that the traction on the deformed body, on this blue body out here? If there is a body in a pressurized chamber, what would be the traction acting on its external surfaces? It would be the pressure acting normal to the surface of that body, right? The pressure is given as P, the normal to the surface is N, so indeed that condition is also checked. So we can see that both the governing differential equation and the boundary condition is satisfied by this particular stress field for a body in a pressurized chamber, which means that it is in equilibrium. Now, the natural question would be that I had this original body sphere, black sphere out here. When I pressurized the chamber, it went down to this blue sphere. The question is how much? How much did it go down by? So how do we answer that? So we need some material property, right? If the material is stiff, the amount of contraction would be small. If the material is soft, the amount of contraction would be bigger. So to connect how much deformation is going to take place, we absolutely do need material properties. And the way that we would solve this problem in a general sense would be basically to try to solve governing these differential equations. We need to solve these partial differential equations. By the way, I hope you see that these are partial differential equations, right? Because divergence operator has partial x1, partial x2, and so on. So these are partial differential equations that we would have to solve as a structural mechanics problem. And the way we solve partial differential equations is that we assume a solution. We assume a solution and we verify whether that satisfies the partial differential equation or not. So in this case, a natural assumption would be that, let's say that the black sphere goes down to the blue sphere, so that the deformation map would be like a uniform contraction, that phi of z is equal to alpha of z. Alpha is some scalar less than 1. And that immediately gives me deformation gradient is alpha times I. C is equal to alpha square I. And I'm missing a tilde under there. Which means that the strain is half of alpha square minus I. And we already know the stress tensor. So stress is minus P times I. And strain is this factor times I. Both I do have now strain on one hand, the strain field, and the stress field. If I could somehow relate these two, then I could express how much alpha would be in terms of P. That's what this says. Right? If I could relate stress and strain, then I could solve this entire problem and say that, okay, if you were to take this black sphere of this material, submerge it in a pressurized chamber, then the radius of that black sphere would decrease by a factor of alpha. Given the pressure P, the radius would decrease by a factor of alpha if I could relate stress and strain, and which is what we'll look at next. Okay, after the next two topics of Kirchhoff stresses. Any particular questions about this example? This example essentially lays out the problem of structural mechanics and how you would solve it. You are given a structure, boundary conditions, loads, and you are trying to verify that it's in equilibrium and that it satisfies all of our kinematic relationships that we had developed before. The only thing remaining would be to connect stress and strain, which is material properties, and we'll get to that in a little bit. All right. So what up until now I've mentioned is that we have been drawing the free body diagrams of a body in its deformed configuration. Now, normally that deformed configuration is unknown to us. If I have a structure, I want to know what that configuration after deformation will be if I apply X or some amount of loads. So that deformed configuration is not even known to me ahead of time. And we have been expressing all our equilibrium conditions. Divergence of X plus B has to hold on the deformed configuration, which I don't know. So this presents a little bit of a problem when you're solving these types of problems, say numerically. So what people do sometimes is that you try to translate all of those conditions. Instead of expressing them on the deformed configuration, you try to express them on the undeformed configuration. You obviously cannot say that I'll draw the free body diagram of the undeformed configuration, and all of those conditions that we developed, the Cauchy stress traction relationship and divergence of S plus B, those do not hold on the undeformed configuration, right? But there are some other related conditions that do hold here, which when transformed to the deformed configuration, give us the same equilibrium conditions that we need. So let's take a look at what this means. So actually, maybe I'll pose this question as well, that the one that I've written here. We know for a fact that if you have a Cauchy stress field in equilibrium on the deformed configuration, the question says, is there a stress tensor field, let's say P of Z? I know that there was S of Z here, but is there a stress tensor field P of Z defined on the undeformed configuration that after going through the deformation process leads to a corresponding Cauchy stress tensor field S that is in equilibrium in this configuration? So the question is there a different stress field P of Z here that becomes the Cauchy stress field on the deformed configuration? And the first question that comes to mind is, what does it even mean to say that that this stress field PZ going through the deformation process to the deformed configuration. So here's what I mean by that. What we are going to do again is to take some part of the deformed body. We are going to consider that, and in order to draw the free body diagram of that part, we know that we would have to go to each point on the surface of that body, compute the normal at the surface of that body, and then apply that normal to this stress tensor. S acting on N would give me traction at that point. So we've been through this for several different types of problems. And to find the total force acting on this small patch dA in the deformed configuration, all we have to do is to take traction times dA. That gives me a small incremental or infinitesimal force. This in the same direction. Okay. Now, what I mean by this this question, is there a other stress field Pz that goes to Sx, is this, that if I consider the same corresponding undeformed configuration, go to the same location, same point on the deformed surface as go to the same location on the undeformed surface, there is a unit normal M there, right? First question, is M the same as N? No, right? We know that M is not the same as N. We derived that Nansen's formula or the Peeler transformation formula that relates area normals to in the deformed and the undeformed configuration, if you remember. So the question now is, we want to have P acting on this M to give me some traction vector. That traction vector, I'm calling it T0. That's a traction vector on the surface of an undeformed body. But the key property is that the traction vector on the undeformed surface times the undeformed area dA should give me the exact same dF as I had here. So that is the important thing to make sure in the definition of this stress field P. So I'll write that here. That dF should be the exact same dF as in the deformed configuration. Okay, the magnitude of the force in the deformed and the undeformed force has to be exactly the same. And why? Because we want the force to be in equilibrium, right? So this force, if it is if it's in equilibrium in the deformed configuration, we are transferring that same force back here. So if this is in equilibrium, no question this will be in equilibrium because it's the same force. And it so happens that this particular stress field P that applied to the undeformed normal, this P is called the first Peeler-Kirko stress tensor, and we will try to come up with a relationship for that. So you remember this was the relationship for equilibrium in the deformed configuration. We're going to write the same relationship in the undeformed configuration. So integral of the traction that we just wrote out, T0 sub M in the undeformed configuration, dA of the undeformed configuration integrated over the area of the undeformed body plus integral B 0 again. This is a body force in the undeformed configuration, d big V, and integrated over the entire body of that undeformed configuration. This expression for force is the exact same as this expression for force. This is in undeformed configuration, this is in a deformed configuration. Okay, and by definition of this stress tensor, I am replacing this T0 with P acting on M. I'll apply this Nansen's formula that we had developed. So on the right hand side, you see that SNDA. We have this term NDA. When we were talking about changes in area, we said NDA was equal to determinant of F times F inverse transpose M dA. I wrote a slightly different formula back then where there was no N. So this this thing F inverse transpose M was in a norm or a magnitude, but here I have that n vector, and I am going to use F inverse transpose as actually a tensor acting on the normal vector. So this is also the same formula. And we also know that dV is equal to determinant of F minus dV. So in that, I will change this expression on the right hand side. I'll write that as integral over the undeformed surface A. S remains as it is. I will change NdA to all of that. So just copy that. Let's see if I can pick out only that. Copy that, paste it here. That's my NdA, which is now written with the Nansen's formula, and plus integral over the undeformed body with body force B, determinant of F dV. Okay. All I did was to just substitute the change of area and the change of volume expressions into this equilibrium condition. And now I'm going to identify certain quantities here. So S times determinant of F inverse transpose. Okay. This is, first of all, what type of quantity is this? Is this a scalar, a vector, a tensor, or what? It's a tensor because stress tensor, determinant of F is a scalar, so let's pull it out of that. So one tensor S acting on another tensor F inverse transpose, right? So that does give me a tensor quantity. This is some tensor times a vector M dA. What do we have here? That tensor P times M dA. So that tensor that we have just said is the first Kirko tensor P, and similarly this B times determinant of F, that is this B dV, B0 dV. So that's this B0. That's the body force, corresponding body force in the undeformed configuration. So Kirko stress tensor is determinant of F times S F inverse transpose. And sometimes this determinant of F is also written as J. So P is J S F inverse transpose. And I'll write that here as this is called the first P capital Kirko stress tensor. And the body force B is the body force in the deformed configuration times determinant of F, which is just simply written as J times B. Okay. J is the Jacobian of that deformation map, deformation gradient. J is the Jacobian of the deformation gradient, which is simply equal to the determinant of F. And it just measures point-wise changes in volume. We know that that's the relationship for changes in volume, right? So B0 is called the equivalent body force. Oops. In the undeformed configuration. And so that those are these two stress, this stress tensor P and the body force B0. These are the stress field and the body force field that we would need to have in order to impose equilibrium in the undeformed configuration, a configuration that we know. Okay. And keep in mind that the way that we derived this was just taking this integral. This was the integral for equilibrium of a body in the deformed configuration. All we did was change of variables from from a unknown deformed configuration back to a known undeformed configuration. So you can also think of this Euler-Kirchhoff stress tensor P as what would result from a change of variables, from a simple change of variables from deformed to undeformed, from X to Z, which you have done many times. I know if you have a complicated integral in terms of X, you do some substitutions, y is equal to some function of X, and you change that entire integral in terms of Y, correct? That's exactly what we are doing here. We have a integral on the deformed configuration which we don't know. We transformed that integral onto an integral onto the undeformed configuration that we do know. All right, so that's basically what the physical interpretation of Euler-Kirchhoff stress tensor is. That it acts on undeformed normals to give me traction vectors. Those traction vectors acting on the undeformed area give me the same force that I would have gotten by the correct traction vector on the correct deformed area. Okay. All right. So let's take a look at what the consequence of this first Euler-Kirchhoff stress tensor is. Just like we had divergence of S plus B on the deformed configuration as an equilibrium condition, on the previous page, right here, you can see I can apply the divergence theorem to this term. What would I get? Divergence of P. But that divergence is not with respect to X. Okay, that is a different divergence, which is with respect to Z, partial of partial Zj, whereas small div was partial of partial with respect to X. Right here, this divergence is with respect to Z. So divergence of P plus B0 equal to 0. That's the new governing differential equation for equilibrium on the undeformed body. If you do sum of moments, you'll come up with a relationship like this: P times F transpose is equal to F pt. For the deformed one, it was a much simpler relationship. S is equal to S transpose, right? Why do we need a more complicated relationship? Because if you see this expression, J is a scalar, S times F inverse transpose. Can you tell me definitively whether Euler-Kirchhoff stress tensor would be symmetric? So first Euler-Kirchhoff stress tensor would in general be not symmetric, because even though S is symmetric, F is not symmetric. F is not symmetric, so F inverse is not symmetric, so F inverse transpose is not symmetric. And of course, the product of those two would make sure that that the first Euler-Kirchhoff stress tensor is also not symmetric in general. So if you do sum of moments, you get a slightly different relationship. And if I just to substitute, just to show you that this sum of moments is the same as the deformed S is equal to S transpose, I'll make that substitution here. P is equal to J S F inverse transpose, and P transpose is nothing but the transpose of all this. So J F inverse times S transpose, which is equal to S. And clearly, if I multiply this out, then F inverse transpose times F transpose, what is that? F inverse transpose times F inverse F transpose, of course, is identity. So this and this just give me identity tensor. Similarly, this F and this F inverse give me identity tensor. What I'm left with is JS on the left is equal to JS on the right. So indeed, it is S equal to S transpose, the same condition that we had in the deformed configuration. Boundary conditions, it's a different Cauchy. This is a different stress traction relationship, and here as well, the boundary has to be decomposed into two parts. Part Dirichlet boundary, where the displacements are specified, and the Neumann boundary, where the tractions are specified. All of those conditions still must hold. Okay. All right. And then finally, since there was a first Euler-Kirchhoff stress tensor, there is also a second Euler-Kirchhoff stress tensor, which people devised just to make sure that we have a symmetric stress tensor. First Vila-Kirchhoff was not symmetric. Second Vila-Kirchhoff is constructed so that it is symmetric. And what is the physical interpretation of that? We know that the first Vila-Kirchhoff P acting on the undeformed normal gives me the traction vector, which leads to this force dF. This force is exactly the same force that you would get by traction vector Tn acting on deformed area. Now, if you were to take this force dF and do the inverse map or apply inverse of F onto this dF, you would get this dF0 force vector, which is just the F inverse of this dF. That's what the physical interpretation of this second Vila-Kirchhoff stress tensor is. dF0 is just F inverse of that dF. And if you go through the relationships, you can show that F inverse, of course, F inverse P would be equal to this sigma tilde, which is the symbol that we're using for second Vila-Kirchhoff stress. And in terms of relationships, F inverse P, we substitute P, we get J F inverse S F inverse transpose. Is this symmetric? F inverse on the left of S and F inverse transpose on the right of S. If I have a symmetric matrix, then if I pre-multiply by some matrix A, some non-symmetric matrix A, and post-multiply by A transpose, the resulting matrix is also a symmetric matrix, right? So indeed, that sigma tensor is a symmetric tensor. The main utility of that is sometimes, to be able to do finite element computations that maybe some of you will look at in the next course or in a future course. The fact that the stress tensor is symmetric helps out in some of those computations, lesser storage, faster solvers, and instead of storing the entire matrix, you can store half or the symmetric part of the matrix. All right, so that's the different types of stress measures. Keep in mind, in all of this, whatever we talked about previously in this chapter about the Cauchy stress traction relationship and the Cauchy stress, that's perfectly valid for small and large deformations. Okay. What we talked about here is a measure of stress that allows you to express that stress tensor, that Cauchy stress tensor, back in terms of a different stress tensor that is described on the undeformed configuration. Looks like my cursor is stuck again. Let me check if that fixes it. Okay. All right. So finally, a small note about stress rates. You remember when we were talking about kinematics, we talked about time-dependent deformations. We were looking at deformation rates and so on. Just like that, for a time-dependent problem, if I have a body that is deforming with respect, of course, to time, changing deformation with respect to time, then the stress field in the body would also be changing with respect to time. And that equilibrium condition that we wrote would actually not be correct. You would need to account for dynamic effects, in which case the right hand side won't be zero. It would be rho density times acceleration at that point, which is nothing but the Newton's second law, right? This statement right here, as I said, was sum of forces equal to zero. That is Newton's first law. If sum of forces is not zero, then it is the unbalanced force is equal to mass times acceleration. That would be the Newton's second law. And for those types of time-dependent problems, even though we are not going to go into too much detail, we would need to calculate and to work with stress rates. How does the stress at a point or the stress field in the entire body change with respect to time? And here's the key problem with that. Cauchy stress itself is objective, which means that if two different observers are observing this body that's deforming with respect to time, and they will look at the stress field, the Cauchy stress field at any particular instant of time, then two different observers, their observation will be consistent with the definition of objectivity. Whereas if the two different observers are measuring S dot, how does that stress at that point change in time? S dot, of course, will be a tensor. That in general will not follow this relationship for all possible different observers. And that means that the stress rates are in general not objective. Just like we saw, velocity itself is not objective, acceleration is not objective, many deformation rates are not objective. So to make the stress tensor objective also, we use the same type of many different types of objective rates that people use to come up with something that is an objective stress rate, so that different observers can relate the stress rates also with the same with their Q transformation matrices. So that's a quick note about objectivity of stress rates as well, just like we had objectivity of strain rates. So I think that pretty much finishes off chapter 3. As I said, I would like for you to go ahead and read ahead in chapter 4 and try to attempt the problems that are given on homework 7. We will not have a lecture on Monday or a review session this afternoon, but I'll be back on Wednesday, and then next week on Friday we'll have a regular review session. Okay? All right, so see you all on next Wednesday.